Hello guys, welcome to Last Hour Mathematics. This is a course I put together for our senior high school students in Ghana. I hope this goes a long way to help you. We pray that God sees us through this course and brings to remembrance everything we learn. Now, I'll be teaching you today resolution of forces. Now, before I start, what is a force? A force is a push or pull that changes a body's state of rest or uniform motion in a straight line. Now, these forces we talk about all the time are classified under quantities we call vector quantities. Why do we say a force is a vector quantity? A vector quantity is any quantity which can be expressed in terms of its magnitude and direction. Now, let me take an example. Look at this ruler. This ruler has a specific mass. Now, when I begin to push this ruler in a specific direction, the product of the mass of the ruler and its acceleration gives us what we call a force. Now, this force progresses in a specific direction. That's the direction I'm talking of. So the magnitude of this force combined with this direction is what makes this force a vector quantity. I would like to start with statics of mechanics, or statics of solid mechanics. Now, assuming you drive a truck across a bridge, the bridge doesn't move, but the truck exerts some kind of weight on the bridge. Now, when we consider all the forces acting on the bridge in such a way that these forces balances each other, presenting no resultant motion on the bridge, then we say these forces are under equilibrium. Now, this is the idea we'll be using in terms of statics of solid mechanics. So when I say statics, what I want to say is all the forces acting in every plane sums up to zero, resulting in virtually no motion of the body in consideration. Now that we understand that forces are vector quantities, let us proceed and explain ways in which vector quantities can be represented. A vector quantity can be represented in graphical form with a line like this, with an arrow. Let's say we have a vector V, so we have V with a wavy line under. This is the first way of representing a vector. A vector can also be represented in component form. Say V equals 2, 3. This is a vector being represented in component form. 3. A vector can be represented in magnitude direction format. As in, let's say, a vector, say V, being equal to, say, 20 newtons, 60 degrees. Now I'll take this and explain all these formats so you understand me. When I draw a vector this way, this point of the vector is what we call the tail of the vector, and this point is what we call the head of the vector. When I measure the distance from here to here, this distance represents the magnitude of the vector. So normally we take a scale, which we'll see later, a scale which is proportional to the magnitude of, let's say, the quantity of in consideration. So if I'm considering a force, I take a specific scale that, okay, let 2 centimeters represent every 10 Newton force, which means that the distance I will measure here should be proportional to the force which I want to represent. So in representing a vector in graphical form with a line and an arrow, the point from here to there, that's the point from the tail to the head, the length of this line represents the magnitude, or is proportional to the quantity in consideration. And when you draw an imaginary vertical line, the angle from this vertical line to this vector line here represents the direction. Normally we measure the angles in clockwise form in a bearing format. So we can say this is a north pole, this is a south pole, we have east and west. So from the north pole right to where the vector is your direction, say theta. But normally in mechanics you wouldn't see these angles, all you will see is the line. But I want you to know there's an imaginary axis here where you can make a reference for your angle. Now, when you represent a vector in component form, what you want to say is the vector v we see here has 2 axis x component and 3 axis y component. So actually the vector is here. So it's going this way. That's from this origin to this point. This is where we have the vector 2, 3. So when I find the magnitude, what I need to do to find the magnitude is to square this 2, square this 3. So I get 4, 9, root of 13. This is the magnitude of this vector. So you can represent a vector in a component form, and from the component form you can know the magnitude of this vector and also know its direction from the north pole. So I can find the angle from here to here to know the direction of this vector v. All we use is simple trigonometry ratios. So we know if we have 2 here, we can draw line here. So if we have 2 here, we also have 2 here. Now on the y-axis we have 3 here, so we also have 3 here. So this angle, to find this angle, I need opposite and my adjacent side, which means I can say that tan theta equals 2 on 3. So theta equals the tan inverse of 2 on 3. And when we find theta, what we derive is the direction of the vector v. So in this format, we can see that this gives us our magnitude. When we measure the line, the distance of this line, it gives us our magnitude, which is proportional to the quantity in consideration. And this, the measuring the distance, the angle from here to there, gives us our direction. Now, when a vector is represented in magnitude direction format, what it means is this is the magnitude, this is the direction. And you see, these angles are always measured from the north pole in a clockwise direction. So what it means is, if I wanted to draw this vector, what it means is I have a 20 Newton magnitude in a direction 060 degrees. This means I start from the north pole, move 060 degrees this way, 60 degrees, and this is my 20 Newton force. So when I write a vector in this format, or I write it in this format, or I write it in this format, it should reflect the magnitude and direction of that vector. Now that we understand the 3 ways of representing vectors, we now know that these 3 ways are also ways in which forces can be represented, because forces are also vectors. Let's now go back to the topic for today, resolution of forces. Now, the question we have here says, resolve forces acting on the particle B and hence find the resultant force. I want to make something clear here. Resolving forces is different from finding the resultant force. What do I mean by that? Resolving a force means breaking up that force into horizontal and vertical components, which I will show you. And resultant of a force means add up all forces on a particle and represent all those summations with only a single force. So we have 10 newtons, 9 newtons, 4 newtons, 3 newtons, 6 newtons with different angles showing their directions. What we want to do is we want to add all these forces, taking into consideration their directions, and represent all those forces just with one force. So the one force stands for all the forces that we see here. That's what we mean by find the resultant of a force. And because forces are vector quantities, we cannot add them algebraically, like the way we say A plus A equals to A. You can't say 6 Newton force, which makes an angle of 30 degrees with the horizontal, plus a 3 Newton force making an angle of 60 degrees with the horizontal, plus a 10 Newton force going vertically downwards, and a 9 Newton force going towards the west, and 4 Newton force going towards the east. You can't add all these and say the resultant force is 10 plus 9 plus 6 plus 3 plus 4. You can't do that because all the forces are acting in different directions. That's why we need to resolve them, and after resolving them, find the resultant using a vector approach. So resolving forces is different from finding the resultant. You need to resolve a force into its components, its horizontal and vertical components, and then you add all the vertical components, add all the horizontal components to see where the resultant of all the forces are going to act, and that's what we are about to do. Now, I want to take you through the resolution. Resolving a force, for example, let's take the 6 Newton force. There is a concept we call triangle of forces. Triangle of forces. What this means is, assuming you have a force, let's say the 6 Newton force we had initially. Can you see? Yeah. 6 Newton force goes in this direction at an angle of 30 degrees to the horizontal. Now, the components of this 6 Newton force behaves in a certain way according to triangle of forces. What it means is, when the 6 Newton force goes in this direction, it would have an x component here and a y component here following a certain sense. And this is what normally happens. When you see the force going downwards, what it means is its x component will always arrive where the head of the vector points. As I told you earlier, this is the head of the vector and this is the tail of the vector. So this is where the x component is going to act. Is going to follow the direction of the head. So you realize that the x component goes this way, so the force in the x direction goes this way, and the force in the y direction also follows that same sense, so it also comes down. Okay, so when you realize the force goes downwards, both the x and y point towards that same direction. That's how they behave. So who can tell me what happens when we have a force going this direction? Yes, you are right. The force in the y direction goes this way, and the force in the x direction will go that way. So we have a force in the y direction and a force in the x direction, and it is the force in the x and y direction which we want to find, and we refer to as components of the force. So we need to find components of the force 6 newtons in the x and y direction, and in fact it is these two forces that combines to give us our 6 Newton force. So let's see how we can resolve these forces. Remember I mentioned forces, the forces acting in the form of a triangle of forces. So this is what I mean. You see this force acting in the x direction, you can transpose it to the top here. So even though it's here, you can bring it up here. Once the magnitude and the direction doesn't change, your calculation wouldn't be affected. So I can bring the force x also here, and you can see what happens. It follows a triangle. Look at the F force acting in the x direction. Look at the direction in which it acts this way, and the y comes down, and the resultant, that's the main force, comes this way. You see, so it follows a triangle. So remember the technique I showed you. Always look at the direction. So when I have a force going downwards, its y component will go this way, and its x component will also go that way. Hope you understand. So let's go back. Before I began, I told you need to know something about trigonometry. We are going to use basic trig ratios to resolve these forces. So first, let's start with the y component of the 6 Newton force, which acts this way. Okay? So when I have a y component here, it means the way I transpose this here means the same thing can also happen here. So I'll have the force going here. So let's start our resolution. Let's find Fy and Fx. Now the directions are very important. Take note. Let's find the Fx. So I have 6 newtons, 30 degrees, and this Fx. So with respect to this angle, this is your opposite and this side is your adjacent. So we need an adjacent in our equation, and also 6 newtons in our equation, and also the 30. So combining adjacent and hypotenuse means we need to use a cosine ratio. So what I can say is the cos of 30 equals adjacent, which is Fx, on hypotenuse, which is 6 newtons. So you need to have an unknown which you want to find. I need to find Fx, so Fx has got to be in my equation with the two other values, 6 and 30, being known. So my Fx will be equal to 6 cos 30. Hope you understand. Let's go to our y component. Our y component is here, so it has to be my equation. So I'll be using opposite and hypotenuse. So I can say sine of 30 equals Fy on 6. So Fy equals 6 sine 30. So this is how I'll represent it. It goes this way. So for the 6 Newton force, you need to draw your x component going this way and write 6 cos 30. Can you see? And our y component going downwards. And what do I write? Y component 6 sine 30. I'll repeat the same thing for the 3 Newton force as you see here. Do you follow? Okay, let's go. Our 3 Newton force, let's divide a page to get some space. I hope you see what I'm doing. Okay, let's go to a 3 Newton force. So I have the force acting here. 3 newtons to the horizontal. What do we have? We have 60 degrees. So as I told you here, look at the sense of direction, triangle of forces. I have my y pointing towards the head and my x also pointing towards that head. Simple. So I'll have my y here and my x here. So my x component goes this way, Fx, so I transpose this one here, transpose that one there. So I have Fy Fx Fy and Fx here. Because my angle is here, it will be better to do my resolution at the top, or I could use the other angle, which will be here, which will be 30. But let's just use the 60, it's easier. So we have 3 newtons here. So let's now identify how to find these forces. Now this side will be my opposite, and this will be my hypotenuse. Okay, so how do I find my Fy? Okay, opposite and hypotenuse. So I can see my sine. Remember, what you need to find, that's the unknown, should be in your equation with the 2 other values known. So I use opposite sine 60, equals opposite Fy on hypotenuse 3. So my Fy equals 3 sine 60. Okay, then let's come to x components, which this opposite, this will be your adjacent, so you can use adjacent and hypotenuse. So what I can say is that cos 60 equals my adjacent, which is fx, on hypotenuse, which is 3. So fx equals 3 cos 60. So what do I say? This fx, what direction does it act? What direction does it? Fx, it goes this way, it goes this way, it goes that way. So what do? I bring it here this way. Can you see? I bring the fx this way, and I bring my fy going up. So we are done with the 6 Newton force and the 3 Newton force. Now let's look at the 10 Newton, 9 Newton, and 4 Newton forces. You see, these forces, I normally call them, this is the words I use. These are pure forces. They are acting in the vertical plane. This is a pure vertical force with no component. It has only a vertical component, no horizontal component. This is strictly horizontal. This is strictly horizontal. So you don't resolve them. This has a vertical component with no horizontal component. So I'll just represent them. So let's label them. This is 1. This is 2. Let's go to 3. Our third force will be this 10 Newton force acting downwards. Can you see? 10 Newtons. And the last last 2 forces, we have a 9 Newton force acting this way. 9 Newtons. And the 5th force is a 4 Newton force acting this way. They are all pure forces. They only have a component either in the y or only the x. So let's proceed. Now that we understand what components of a force are, let's proceed and solve the first part of the question. We're told here to calculate, or let me say, resolve the forces acting on the particle B. So we now have the components of the force, which means we've resolved all the forces. We've done the first part of the work, but we need to proceed further and simplify it. So what did I have here? I had 6 sine 30 here. So what will it be? Let's take our calculator. 6 sine 30. I know you can't see what I'm doing, but no, everything here is wiped off, but I can see. 6 sine 30. What do we have? 3. Then 6 cos 30. 3 root 3. Then we go to our second part, 3 sine 60. 3 sine 60. That's 3 root 3 on 2. So I have 3 root 3 on 2. Then 3 cos 60. (1.5) 3 on 2. So 3 on 2. These are pure forces, so we wouldn't resolve them. So now let's add all our x components and all our y components to get the resultant component, because you see we've been told here also to calculate for a resultant force. What we just did now is for the first part, that's resolving the forces. We've resolved all the forces. So in component form, this is how our forces are going to look like. We are going to have the first part, that's the x component, 3√3. The y component as 3. We get to the second part, our x component is 3/2. 3/2. And our y component is 3√3/2. The third part is a 10 Newton force which has only a y component, no horizontal component. So x component is 0 and the y component is 10. Then the fourth one is 9 Newton. It has an x component with no y. So I have 9, 0. And the last one has an x component also with no y. So I'll have 4, 0. So these are the components, but we need to add certain signs to them. You know, there's a convention in mechanics. When forces act upwards in the y direction or in the vertical direction upwards, we assign them to be positive. When they act on the x-axis towards the right side, we assign them also to be positive. When they act along the y downwards, we assign them to be negative. When they act on the x-axis in this direction, we assign them to be negative. So you see, let's go back to our forces. This x component force here, which was 3√3, acts in this direction. So on my paper, I'll sign it as a positive force. Its corresponding y component acts downwards. Okay, look, I'll sign it as negative. When we come here, the x component here acts in the positive direction. So I'll make this positive. And the y component here acts upwards, which is also positive. Now, let's go to the 10 Newton force. It acts vertically downwards, which means I must negate it. This is already 0. Let's go to the 9, acting in the negative direction. So I'll negate this 9. Can you see? This is acting towards the positive side, so I'll make it positive. So these are the components. You can reduce these ones to decimals, okay? But I want to keep it in this state so accuracy is more defined, so that accuracy will be maintained. Okay, so let's see, this is what we have here. You get it? So these are the components. So we'll solve the first part of the question, which says that we should resolve the forces. That's what we've done. We resolve all the forces into x and y components as the horizontal and vertical components. Now, when we try adding these forces, what we will be doing now is finding the resultant force. So let's go. So, before I proceed, let me explain a concept. Now, assuming I didn't want this body to move, this body B, I didn't want it to move. Imagine the body hasn't been hinged under the action of these forces, so it's like free to move and under these forces. Now, I want to see the overall effect of these forces on this body. So ideally, if you want a zero effect on this body all the x components acting on the body, that's the forces in the x direction, ideally should sum up to 0, with the y forces, that's the y component, also summing up to 0. This means the body is in static equilibrium, which means that the forces cancels out to keep the body where it is. So let us investigate and see if indeed there will be a resultant effect on this body due to these forces. And remember, in statics, the assumption is this body doesn't move. So let us see if this body will indeed move. If it moves, we tweak the question to see what actually this means. So let's see. So we add all our x components. So I have 3 root 3 plus 3 on 2 plus 0 plus a negative 9 plus 4. This gives me in decimal form 1.696. This is a chopping off approach. So I chop off these values and it leaves 1.696. That's okay. Then let's go to our y components. Have negative 3 plus 3 root 3 on 2 minus 10 plus 0 plus 0. So you see, these signs are very important. When you get them wrong, your answer will be wrong. What do we have here? Negative 10.401. So you see, when I added all the x components, it didn't give me 0. When I added all the y components, it didn't give me 0. This means there will be a resultant force acting on the body. So if this body is not hinged, you would have motion. Okay? This body wouldn't be stationary if it is not hinged. But what does this mean? Is it possible that these forces is what's producing this effect? So do you know what we'll do? Normally in your questions, let's say a question like a light inextensible string holding a certain object inclined at an angle to the horizontal, those questions are based on statics. The assumption is that the total forces acting on the body is 0, but this is a real-time situation. So we have to design it in such a way that these forces acting on the body will produce a negative, like a 0 effect on this body to prevent it from moving. And that's the concept of statics. So at least with this question, you've understood that with resolution of forces, you could determine if the forces could have a resultant effect on the body or not. So do you know what we're going to do? We are going to change this 6, we raise it off, represent it with a variable, change this 3, represent it with a variable, and calculate a specific force that will keep this body at rest. Hope you get me. So let's go. So please, just before we proceed, let's complete our question. It was said here that we should find the resultant force. So now we have the resultant force, that's the components of the forces. So we could add all these x components to get the overall horizontal component, add all these y components to get the overall y component. Then after, we could leave our answer that way because we could express the resultant force as a component or the resultant force in magnitude. But you see, because... Okay, let's quickly finish up. We're told here to find the resultant force, okay? So at least we should find the magnitude of the force because you see the question stated all the magnitude. So if you are asked to find the resultant force, you also need to find the magnitude of the resultant force. We've done most of the work. We've expressed the forces as components. So So when we add all the horizontal components, that's the x components, and we add all the vertical components, that's the y components, it means we've got the total resultant component, not the magnitude, total resultant component. Okay, so in a way, you remember when I was trying to explain how we could represent vectors, and I explained that we could represent it with a line and an arrow, and also represent it in component form in magnitude direction format. What we will do here, if we add all the x and all the y, what we arrive at is representing the resultant vector in a component form. We will proceed and find the magnitude and leave our answer that way. Or let me add it this way. I will also proceed and show you how to represent that same vector or that same resultant force in magnitude direction format. So let's go going. So let's quickly add these. We have 3 root 3 plus 3 on 2 minus 9 plus 4. Can you see what I'm getting? 1.696. Do you know I'll be chopping off, so I wouldn't be rounding, I'll just be chopping off, so I'll just write 1.696 and leave all these ones there. So it will be 1.696, so equals 1.696. Then what else? Negative 3 plus 3 with 3 on 2 minus 10 plus 0 plus 0. That leaves me with negative 10.401. Remember, I'm chopping off all these ones. So this is our resultant component. After resolving these forces, we've got our resultant component. So now let's find the resultant force. That's the magnitude of this. So this is our R. So to find the magnitude of R, what we need to do is to find the square root of this x component, 1.696 squared plus negative 10.401 squared. So let's see. The root into bracket 1.696 all squared, can you see? Plus negative 10.401 bracket close all squared. Can you see? Can you see? So this leaves you with 10.538. Chopping off all this. Newtons. Of course, in a typical question, you'll be told to round, let's say, to 2 decimal places. So all you do is round this 8, take it here at 10.54. But I need accuracy, that's why I'm chopping off. Okay? So let's get going. We found the resultant force. We are officially done with this question. But I want to proceed. We've represented this resultant force in component form. Can we represent it in magnitude direction form? Yes, we can. From the components, we could do that. Remember, the only thing that differentiates them is this is in component form. But in magnitude direction format, you need this magnitude and the direction also. Okay? Remember, even with this, it tells you the direction because you have to sketch. You have a positive side on the horizontal, a negative side, and it shows you the direction in which the force is going. So assuming I wanted to sketch this, I will do this. So I have 1.696, this is not to scale, and negative 10.401. So you see, this is where I have the 1.696, negative 10.401. You see, it gives me the direction where the force is going. Okay, so even this produces the direction, but we want to specify this resultant also. Remember, this is just a bonus. I want to explain how we can also specify the resultant force in magnitude direction format. So let's see. I would have to sketch it this way and calculate my angle from the North Pole to where the force is. Okay, so remember these are quadrants, so this side is 90. We could find the angle here, then we add it to 90 to get the bearing formats for the force. So my force, as my resultant force, is 10.538 Newton. Remember, you'll be asked to round to 2 decimal places or something. So we are left with our angle. So this is our angle from the North Pole clockwise to where the force is, where the resultant force is. So let's calculate this angle. So let me sketch it here. Remember, we don't need a negative sign when we are calculating for the angle. Okay. So we have 1.696 for the x and 10.401 for the y. So to find this angle, I need my opposite. This is the opposite side to the angle. This is the adjacent side to the angle. So what do I have? Opposite and adjacent. That's tangent. So I can say, let me write here, my tan of my alpha equals opposite, which is 10.401 over my adjacent, which is 1.696, opposite over adjacent. So my alpha equals the tan inverse of 10.401 all on 1.696. So my alpha equals what? The tan inverse of 10.401 over 1.696, close. That's 80.738. 80.738. Remember, again, I'm chopping off. So I've chopped off all these ones here. Now remember, we don't need the alpha. We need alpha plus 90. So I take my answer plus 90. This gives me 170.7. Okay? We could write it as 171. So my total direction is going to be what? 80 plus 90, which gives me what? 171. So this is how I would have represented my resultant force in magnitude direction format. And this is how I would have represented my resultant force in component form. So now let's go back to what we said. We said we wanted to represent this and this with variables and calculate the actual value of F, which will make this remain at rest. Remember, I'll be treating resultant of a force in my next video. Okay, I'll dedicate the next video to resultant of forces. What we just did was for me to introduce you to how to find or how to resolve a force into its corresponding components. Thank you. Let's proceed. So let's go to the second question. This will be our last question for this video, and hopefully I'll be doing another video on resultant of force fully dedicated to it. Now, in the last question, we resolved the components and found the resultant component. We realized that this component tells us that our body here wouldn't be in equilibrium, because in statics, what we were expecting that for this body to stay at rest, all the components in the x and y direction should sum up to 0. I mean, at least with this analysis, we know that if this body B here is not bolted or held, it would move, because a resultant force which has a 1.696 component in the x and a y component of negative 10.401 would act on the body, which will prevent it from staying at rest. So I've designed the question in another way, and look at what it says. Calculate the values of F1 and F2 that will keep the body B at rest. So this question is telling us that, look, I don't want to bolt this component B. I don't want to hinge it. I just want these forces to balance this body B. In fact, these forces should act on the body B in such a way that the resultant force acting on this body would be 0. Okay, so we'll go through the same resolution, okay, to find F1 and F2. Sorry, this is F2. You get it? Okay, so let's proceed. So I'll do the same thing. I'll sketch and indicate where these forces are going. So let me put this here, and hopefully I hope you see. So let's take the F1. F1 is going this direction. Can you see? F1 30 degrees. So our y component for this F1 will go this way, so F1y. Then we have our x going this way, F1x. Remember what I told you, the x and y components acts towards the head of the vector in consideration. So we said we could put the F1y here and the F1x here. So let's find these components, okay? So let's see. Now, what would this F1x be? I could use, this is F1, this is 30. So what do I say? What should this x component be? I could use, this is opposite, this is adjacent, this is hypotenuse. So I could use the adjacent and hypotenuse. So what do I say? The adjacent and hypotenuse is cos. So I'll say the cos of 30, can you see? Equals adjacent, which is F1x, over hypotenuse, which is F1. Which means F1x equals F1 cos 30. If you should do the same thing for this y, you would have opposite and hypotenuse, which would give you F1y equals F1 sine, cos is opposite over hypotenuse. So if you do that for this, you get F1 sine 30. Remember, take into consideration their direction. This is going here, so it will be this way. Okay, this is coming down, so I put it this way. Can you see? Let's go to 3 Newton 60 degrees. Sorry, we changed it to F2. So I'll have F2 60 degrees. So this side will give me my y. Remember, they act towards the point. So I have F2y, F2x. So let me close up. Okay. So F2y will also be here, and F2x will also be here. Let's focus on this side. So to find F2x, remember this will be my opposite, this will be my adjacent. So using adjacent and hypotenuse will help you to find your F2x. So what do I say? Can you see? Cos of 60 equals adjacent, which is F2x over hypotenuse, which is what? F2. So I have F2x being equal to F2 cos of 60. When you do that for F2y, you'll be using a sign opposite on hypotenuse. So you'll be having F2y equals F2 sine 60. Now let's indicate the direction. This one is going this way. Remember, the directions are very important, and the y is going upwards. So we label it again. This is our 1. This is our 2. What is our 3? Our third force. That was a 10 Newton going down, which we didn't change. Remember what we did? We changed this 6 newtons to F1, changed these 3 newtons to F2 to see those exact values, which will give us a resultant force of 0. Okay? Can you see? Okay. 10 newtons. 4. What do we have as 4? 9 newtons going this way. And 4 newtons going that way. And remember what I told you? I told you when you have the force going up, it's positive, coming down, it's negative, going here, it's positive, coming here, it's negative. So please take note of this. Okay? Can you see? Can you see all that I've done here? Because I'll be going to the next. Can you see? Okay, let's go. So we add all our x components and add all our y components. So let's see. This is our x component going towards this side, so it will be positive. So I have what? I'll have F1 cos 30, which is positive. Can you see? Come to this second one. This is the x component, which is what? F2 cos 60. Where is it going? Also going to the positive direction. So I'll do F2 cos of what? 60. Can you see? Now let's look at other x components. So we are taking only x components. We're taking this, we've taken that. Now let's go to this and that. Those are the two remaining x components. Now this is an x component but going towards the negative side. So it will be negative 9. Can you see? And this is going towards the positive side. So positive 4. In statics, we don't want this to move. Okay? We said we didn't want this to move. This object B to move. So if you don't want this object B to move, all the sum of the x forces should be equal to 0. All the sum of the y forces should be equal to 0. So we equate this to 0. Okay? Then we go to our y components. This is our first y component, F1 sine 30. And where is it acting? Downward. So it's negative. So negative F1 sine 30. We go to our second question, our second resolution is going upwards. Look, going upwards. So it will work positive. Positive F2 sine 60. Okay. Then what other y component do we have? This is the last y component, and it's 10. It's going downward, so we need to what? Negate it. So minus what? 10 should be equal to 0. So these are the two systems of equation we'll be solving to find our F1 and our F2. So let's see. What do I have here? Cos 30. Cos 30. Cos. Can you see? Cos 30. Root 3 on 2. So what I have here as well? Root 3 on 2. F1. Okay? So, let's write them in decimal, okay? So let me change it to decimal, 0.866. So 0.866 F1. Then let's do our cos 60. Cos 60. That's 0.5 plus 0.5 F2. Negative 9 plus 4 gives us what? What does it give us? 5, 6, 7, 8, 9. Negative 5. So minus 5 here, take it here, we get positive 5. Then we come to our sine of 30. Sine 30. That gives us 0.5. So I have 0.5 F1, but remember it's negative. Okay? Then I come to sine of 60. That's 0.8660. 0.8660 positive F2. We send this there, we get 10. So this is my first equation, and this is my second equation. So let's go to simultaneous equations, and let's go for equation 5 and 1. Okay. So what do I have here? 0.866. 0.866 equals 0.5 equals 5. Come to the second one, negative 0.5, 0.866, 10. So I get my F1 to be negative 0.6700 and my F2 to be 11.1604. This is in newtons, this is also in newtons. So what this means is, for this body to stay at rest, you need F1 to be negative 0.6700 newtons and F2 to be 11.1604 newtons. Okay? Okay, so these are the forces that will make this body stay at rest. So what you need to do now is, let us explain, what does this negative mean? If you do a resolution or you solve for a force and you get a negative answer, what it means is the force moves opposite to the direction in which you assigned it, for this condition to be maintained, the force must be negative, which means instead of me representing this F1 going this direction, this is the direction in which it should go, and it should have a magnitude of 0.6700 Newton, and the F2 should be 11.1604, which its direction should be maintained. It is these two conditions that will keep this body at rest. So what is this? What the answer wants to tell us? What it wants to tell us is that the F2 should go in the same direction because it's positive here, which means the direction we assigned is good. So 11.1604 newtons is correct, but this force which was initially going downward should go up this way and have a magnitude of 0.6700 newtons, with this one still being negative 10 newtons acting downwards, 9 newtons acting here, and 4 newtons acting here. These are the conditions that will make this body stay at rest. Okay, so you now understand how to resolve components, how to represent forces in different form with a line and an arrow, magnitude, direction format, and in component format. Now you can interpret your answer. When you get an answer which is negative, an answer which is positive, you understand what they mean. Okay, but remember, in solving other forces, let's say there was an extension of this question and you are supposed to solve other forces. After you get this negative force, never make it positive. Maintain your answer true till you finish all your questions. Okay, so thank you so much. Meet me in the next video. Subscribe and let's look at how we can find resultant of the forces. I'll be treating a lot of things in your syllabus, so kindly subscribe and let's get going. Thank you.